without further ado, let's welcome Udbhav here, and he's going to take a deep dive into Rails server.
All right. Thank you very much for the introduction, Gautam. All right. I hope everyone enjoyed their tea break. Yeah? I also hope you didn't have something heavy for the breakfast, because now I'm about to serve you something even heavier. The internals of Rails and Puma. Yeah. Quick show of hands, how many of you are on Rails server recently? People have not started Rails server? Come on. Nice, nice. Very good, very good. Now, how many of you know what actually happens when you slam that enter button, like your life depends on it? No? Good. That's why we are here. A quick introduction about myself. This is Udbhav Gambhir, senior engineer at ThoughtSpot. I work in building and scaling backend systems. Across the internet, I am better known by my username, Udbhav. You can find me anywhere from udbhav.com to GitHub, LinkedIn, etc. Let's. Yeah, you can find me there as well. Let's start, shall we? All right, what's your favorite way to start the Rails server? Me personally, I use Rails server. My ex-manager introduced Foreman to me. He used it very heavily. Then I am also aware about Puma Dev. It's the official tool developed by the Puma team to start the Puma in development mode. Bundle exec Puma, either directly or via systemd. It's generally preferred in production or containerized environments. Any other command you guys use? And before you say anything, please do not say command aliasing or bundle exec prepending. Yeah, because I'm a little short-tempered person. Yeah. Just kidding, I'm the complete opposite. Any other command you guys use to start Rails server? No? Either way. Let's first look at what happens when you start Puma via Rails. All right, I think this is running a little faster. All right, so the first step that Rails does is it sets up the signals first, because it needs to gracefully exit when you hit the Control-C button. What are signals, you ask? A signal is an asynchronous notification that is sent to a process to inform it of an event, right? For example, Control-C or SIGINT. It's a hardware event signal. Once the signals are set up, the next step is to set up the directories. Some very specific directories are set up by Rails. For example, cache, PIDs, as in process IDs. The next step is to set up logger. This is facilitated via our favorite active support. You guys remember active support? Good, lot of yes now. All right, our favorite active support where the .present method comes from. Very regularly we use it. Yeah, that's not a native Ruby method, just saying. The next call is rackup server start. This is interesting. Rackup server start will pick the first available server out of the three, Puma, Falcon, and Webrick. This is an order. It finds that the Puma gem is installed, and it calls Puma rack handler run. Right? Once the control flow reaches Puma, Puma can now take things forward. Right? My question is, rackup and Puma, these are two different libraries. Right? How did rackup know specifically which class to call? Right? I'll show you a code snippet which will help answer the question. In short, what this code does is, if rackup is defined, it will use rackup to register Puma, else it will use rack to register itself. In long, it first searches for rackup module, a global rackup module. And then it will search for handler module within the rackup module. Once both the conditions are met, Puma will move on to define a module Puma, which will then register itself. The else case more or less does the same thing. However, in the else case, instead of rackup, it will use rack to register itself. I'm going to throw a question at you just to check that none of you are sleeping. Why the if-else condition? Isn't rack supposed to be a consistent framework for servers for request and response? What's with this inconsistency? Think about it while I grab the laser pointer. This slide will help you answer that. Look at that comment on top right. Rackup was removed in rack 3, it is now a separate gem. This comment is made by Puma. And before you question, this is the official source code of Puma. So do not question the integrity. So with rack version v3 release, rackup and most of the server-related components were moved out of rack into a separate gem called rackup. Now, since these are now two separate libraries, the registration process of web servers have slightly changed. You'll notice this pattern across both Puma and Sidekick and all the other servers that directly depend on rack, right? Let's talk about Puma. Yeah, no, not this Puma. They didn't sponsor us. No, I don't see them. I even wore Puma shoes for today. But, OK. This Puma. How many of you are seeing this logo for the first time, by the way? Yeah, you guys need to open GitHub regularly. All right. Puma, as we all know, is a simple, fast, well, not so simple, fast, highly parallel HTTP server for Ruby rack applications. You guys would be familiar with this log? Yeah? Rails starting in cluster mode, Puma version, Ruby version. By the way, Puma version 6, Puma version 7 is out now for over a week. Go check that out. That's really interesting upgrade. Then it says environment, PIDs, preloading application, and then listening on the default port 3000. Once the control flow reaches Puma, wait, let me rewind you a bit how the control flow reached Puma. Once the call was made to rackup server start, it called Puma rack handler run, which in turn called Puma launcher run. The Puma launcher run, this is now the main entry point of Puma. Going forward, either you start Rails server via Puma or Puma CLI or anything. This Puma launcher run is now the main entry point. So what this does is, Puma launcher run will start all the plugins first. Plugins, I'll share an example with you. Systemd, it's a default plugin offered by Puma team. It allows your Puma to start the Puma as an operating system service. Of course, you can turn it off. The next step is to set up the signals. Some signals like sigterm, sighub, and some custom user signals like siguser1, siguser2, etc. One interesting thing that I found out while wondering about the Puma code is, if Puma detects itself running under JRuby, it skips the handling of siginfo. Why is that? JVM already handled siginfo for us. So Puma decides not to intervene. I mean, why? The next step is to set up the process title. Process title setup is important to let users know what's going on. I mean, either via task manager or PSOX command line utility or other tools that you like. The next step is really very interesting, and this is the heart of Puma. Depending on whatever the runner class is, the run method is called. We'll come back to that runner class a little later, and let's dive in the run method for now. Because apart from some nitty-gritties, more or less the usual work is same. All right, so the run method will try to load the entire application first, and then start all the background plugins. It then starts the control server. What's a control server? In the official documentation, the control server is sometimes referred to as a status server. A control server is like an admin tool for a Puma application. You can stop, restart, phase restart, and perform some other actions directly via a simple web interface. Puma CTL CLI can also be used to control this control server, if you will. Just a quick sleep check. How many of you knew about the control server before today? No? No one? All right. You made me the happiest man today. The next step is to start the web server, where when the main web server is started, Puma will begin listening for the request. For some people who have not wondered about how the web server code looks like under the hood, I've copied some code snippets from Puma. All right, look at this. A simple infinite while loop. This loop allows the web server to wait for the incoming request. And once a request arrives, it will call the handle request function. This handle request function will handle the request. What this does is, it will Puma perform some basic checks, add some variables or data, and then Puma will forward the request to rack via app.call env. There's a problem though. If we go by this idea, one running Puma can only handle one request at a time, right? At scale, we would need many instances of Puma running at the same time to handle the load. It appears we have a classic scaling problem. Yeah, I love minions a lot. Let me share an example with you. Let's say that you have to handle a maximum load of 10 QPS, or request per second, whatever unit you like favorite. To handle a load of 10 QPS, you would require a minimum of 10 instances to serve every client peacefully. Right? The solution? Multi-threading. How about we open a thread to handle a request? Puma will keep listening on the request, and once a request arrives, it will assign one of the open threads to handle the request. This way, Puma can handle multiple requests at the same time. Right? Simple. What about memory usage? Look at the image in the figure 1. The memory usage will be equal to the static memory added to the number of threads times the processing memory. Of course, we are increasing memory usage, but we are also increasing availability. I mean, why won't we want to do that? But there is a different problem. See the sad minion over there. Multi-threading comes with a lot of disadvantages. The first, infamous GVL, or the Global Virtual Machine Lock. Some people like to call it GIL, or the Global Interpreter Lock. It was removed in Ruby 1.9 when a new VM was introduced. Since then, the correct terminology for over a decade now is GVL, or the Global Virtual Machine Lock. The Global Virtual Machine Lock is a process-based lock. So global is in the same sense as a global variable. The GVL states that at any given point of time, in a single process, only one thread can hold the GVL. So parallelism is limited to I/O in Ruby, right? There's a great article written by Nate, maintainer of Puma, that explains a lot about GVL, history, and the benchmarks. I'll see if I can get the link to you guys. The next is the race conditions. Ruby, a Rails code in itself is thread safe, but your code may not be. You do not want to send unintended emails to unintended users, right? And get some support tickets on the same. You do not want to schedule a one-on-one call block with your manager. Fault tolerance is also questionable. If one of your threads sec faults, your entire process is gone and doomed, right? The solution, multiprocessing. Multiprocessing, on the other hand, is a viable option because it solves all of the problems with multithreading. The GVL is not valid here because it's a process-based log. Race conditions are also not valid because each process gets its own memory space. So one process cannot essentially corrupt the memory space of any other process in ideal scenarios. I mean, we are not talking about malwares and all. The next is fault tolerance. Fault tolerance is also, very helpful here because if one process dies, the another process has to independently die for a complete downtime, right? But then every coin has two faces. Multiprocessing comes with one disadvantage, that is the increased memory usage. This time, the memory usage is equal to the number of processes times the static memory plus the processing memory. That's like a huge addition of memory usage, I would say. For example, let's say that your Rails application requires 100 MB of memory to boot up. With multiprocessing, with 5 processes, your application would consume 500 megabytes of memory at boot time. And that is without serving a single request. Isn't that a huge wastage? What if there was a way we could share this static memory, which is common to all the processes? Enter copy on write. By the late 90s and early 2000s, all major operating systems began supporting copy on write. The idea is simple. The idea is to share the static memory across all of the forked processes. The shared memory or the static memory will be available to be read and utilized by all of the forked processes. The static memory will only be duplicated when a process tries to write over it. The memory will be copied over, and then the process can write over its own memory space. This time, the memory usage is equals to static memory plus the processes into processing memory. So we have saved a huge chunk of static memory here. Going back to the example previously, we saved almost 400 megabytes of memory directly. Have you guys seen that frozen string literal true magic comment on top of some Ruby files? Yeah? Nice, nice. All right. You may have also noticed that we try to freeze strings and constants in Ruby and ensure they're immutable always. Can I get another yes? Nice, thank you. So, one major advantage that this immutability provides us is delaying or preventing the copy on write as much as possible. Because this is not only memory effective, but also time effective. Copy on write is a costly process, I would say. Now that we know a lot about why multi-threading and multi-processing is important, how does Puma utilize it? Let's come back to Puma. Remember when we talked about runner class and that we'll come back to it a little later? Now seems to be a good time. Depending on what runner class, what mode Puma you are running on, runner class can be either equal to Puma single class or a Puma cluster class. In clustered mode, Puma allows spawning multiple processes or workers at the same time. Puma team recommends keeping the number of workers to be equal to the number of cores present in the system. Very recently, they have tuned the number of threads to be equal to 3. You remember the run method? It loads the entire application first, starts all the background plugins, starts the control server, and then the main web server, which then traps itself in a while loop, and then it will start to listen our request and then call the handle request function, right? In the clustered mode, after the main web server is started, Puma spawns on to begin multiple workers using this code. This is a high-level code. I mean, a lot more happens behind the scenes, but you can call it like a high-level flow, or some people would like to call it gist, right? I'd like to end the session by shooting a question at you as a homework. What happens behind this fork process, behind this fork system call? How is it possible that all of the worker processes and the master process are able to listen at the same port without raising any error? And how is it decided that which process will pick up the incoming request? All right, hopefully the next time you run Rails server, it won't see a magic, you won't see a magic, and you will be able to appreciate the orchestra behind the scenes. Thank you all.